Hello everyone. So today I'm gonna try to implement a method that will automate the solar cell device optimization process using machine learning. So let's look at the problem first. A lot of times we have multiple new absorber materials and we want to test it with multiple ETL and HTL materials, which is a lot of hassle as we have to do a lot of SCAPS calculation and manual data analysis to get the best device. So I was thinking if we could develop an ML assisted optimization process which will automate all of this stuff and get you the best device while you just have to initially configure some things and the uh, model will do all the stuffs for you. So let's look at the plan of what we're going to do today. So we need to do some initial preparation such as the naming conventions and making the device materials separately. I'll go through all this process. Then we will have to set some optimization rules. For example, the range of thickness between which the model will try to optimize the device, the best device. And then the model will generate a new dataset. Based on this dataset, code will modify the SCAPS files and then run the SCAPS simulation based on these inputs. After that, some results will be found and the model will store the results and compare and learn from these results and see whether the model is still improving. If it's still improving, it will generate new dataset again. And if the model sees that if it's not further improving that much, then it will output the best devices. So let's look at the initial preparations. So we need to save every layers individually as .material file and use prefix like absorber underscore ETL underscore HTL underscore for naming convention. For example, ETL underscore titanium dioxide dot material. So let's see how that works. So now I'm opening my SCAPS program. We need to save every material separately. For example, I have already saved a lot of materials, and for example, the HDL, you can load it like this. So you have to name HDL like this, like you have to write HDL underscore cu2 and then save this material as HDL underscore cu2o. Similarly, you have to save all the other materials like the absorbers and ETLs, the ones you will be needing for this analysis. You have to save all the materials separately and name them like this. For example, if I load this, we have to write absorber underscore the absorber name in here, and while saving, you have to write absorber underscore the absorber name dot material when you are saving it. And then you have to make at least one device. So I have already saved a lot of devices, so you have to at least make one device that will have those names. So number two is design a device, make sure it runs, and save this design as .scaps file with save all settings button. For example, yttest underscore all underscore settings dot scaps. As you can see, I have already constructed a device with all the naming conventions, and make sure the maximum number of iterations is 1000 1 million and Press OK and make sure it runs. So my device is running OK. It gives all the IV characteristics, and now you have to save this setting by pressing save all settings, and you have to name it for this tutorial. To follow this tutorial, you have to name it like this: YT underscore test underscore all underscore settings dot scaps, and save it. Now I will be providing you with a SCAPS script, and you have to place it inside the scripts folder of SCAPS. To know where the scripts folder is, you just have to right click on your SCAPS application and press open file location. And you'll see here that there is a folder called script, and I will be providing you a script file. You have to just copy it from my repository and paste it inside this folder, like here. Now you have to do some minor code modifications. Let's go back to our SCAPS installation directory by opening the file location, and inside the SCAPS installation folder, just make another folder, name it however you like. I'm naming it as ML optimization test, and inside that folder you'll have to just copy this ML automation.i2nb code and paste it right here. Now I will be using Visual Studio Code uh, to edit this file. You can use Anaconda, so you have to have Anaconda installed in your computer. So first of all, you have to uh, search for Anaconda prompt. There it is, and you have to navigate to your SCAPS installation directory. So I am currently inside C, so I'll have to navigate to this folder. So I'm copying it as directory and pasting it in here. Oh, just I need to press F first. So now I'm inside this directory, and I'll do it one more time. Yeah, now I am inside this directory, and I need to open Jupyter Notebook here. So Jupyter, there is my create folder, and this is my code. Now you'll have to start modifying this code in several places, but personally I use Visual Studio Code, so I'll be editing my code using that. So I'll just right click and open it with Visual Studio Code. So these are the libraries you need to import, and first of all you have to make a dataset, and your columns will be like absorber thickness, HDL thickness, ETL thickness, and absorber acceptor density, and HDL acceptor and donor densities. And you'll have to make columns for VOC, JSC, FF, and power conversion efficiency. And for the absorbers, you have to write the names that you have inserted and save your file. Like in here, you have to write this only this portion in these places. So for the HTL, write the names exactly as you have written them inside the SCAPS, and same for the ETLs. And here you have to specify the range between which the model will try to find optimal parameters. For example, I have chosen to start from 0.05 and up to 3 micrometer for absorber thickness, and similarly for the other thickness and the doping concentrations. You have to specify this similar range in another place, down here somewhere. Yeah, right here. You have to do the same range specification in here as well. So after that, it will prepare a data set with those column names, and it will generate 10 instances randomly as an initial starting point, and place those IV parameters as 0 for now. Next, will have to generate our initial data and replace the zeros with the actual simulated values. So if you remember earlier, we have saved a SCAPS setting like this. If you see here, the problem file is yttest all settings.scaps. It's inside the dev folder. So let's go inside the dev. Let's go and see what the dev folder is. So this is my installation directory of SCAPS, and this is my dev folder, and there is my yttest all settings.scaps. So our code is inside this folder. So we'll have to go one directory up to be able to be here, and we'll have to go inside this tip folder and find this name. So this destination file does exactly that. And this function update definition file will go inside the materials file that you have provided. And so where are the materials file? The materials file is inside this materials folder. So that code will use these material files and modify the SCAPS file, modify the based on those material files. So this will read the materials files individually, the absorber, ETL, and HDLs, and this function will actually run these SCAPS. So you'll have to write this script file, which you have copied earlier in the scripts folder, and the results directory you will have to specify like this, and you will also have to specify the output file, which I have written the output file as this. So if you want to follow this tutorial, you will have to write the output file as exactly as it's shown in here. And then another important thing is that your SCAPS version might be different from mine. So uh, let's see which version of SCAPS am I using. So this is the my SCAPS execution file, uh, and the version is 3310. So you must write the version name exactly as is. Yours might be 3312 and 3311 or whatever. So you have to write according to that. And it's several places actually, so you have to update the code in several places. You can use the search and replace functionality to do that in here. So 0 and replace it like this in all occurrences if you like. So and then as the program will run, and it will be getting the output results, the VOC, JC, FF, and ETA. So it will store those output files inside the data set that we have created earlier. As you can see, it's using the prefixes observer underscore htl underscore etl underscore everywhere. So you must name those materials like that in the SCAPS file. So after running with the 10 dataset, it will save the instances in this CSV folder. So let's go ahead and run the code cells up until this point. So I have imported all the libraries. Now I'll be making the dataset. The dataset is complete. As you can see, uh, I have created 10 instances of uh, the 10 different kinds of device structures with a random thickness, but within that range that I have specified earlier. And initially, it has placed all the VOC, JSC, FF, and EWs as 0. So now in the next code cell, it will run these devices inside SCAPS, and it will store the IV values in these cells. So let's go ahead and run this code cell. So while you will be running this code cell, the SCAPS window will pop up and close constantly 10 times. So you'll have to be patient uh, and sit back and just let the code do its job. So as you can see, the code cell has just completed its execution, and an initial data is generated and saved to updated instances.csv, as you can see right here. Now let's go ahead and get into the main part of our workflow. So in here, if we go back to our slide, so we are up to this point right here. So the model will learn from the results, and it will generate, if it's still improving, it will generate new data set based on its experience. And if it will keep doing this loop until it's not further improving, and it will generate the best devices. Now if we go back to our code, let's see if there is anything we need to change here. So we have already talked about this range, and so there are two important variables, as you can see in here. The first one is tolerance, and the second one is patience. So tolerance of 0.01 means that at least this much improvement in the PCE is required to be able to call that an improvement. Otherwise, it will not consider the improvement significant. And the patience equals to 10 is it will it will iterate 10 times to see a significant improvement. If the model, after iterating over 10 times, does not see a significant improvement, it will make a decision and uh, output the already best result as the final optimized device. And this portion will save uh, the instances of after every 10 trials. So let's go ahead and run this code cell as well. This code cell will also make the SCAPS window pop up and close down multiple times. It will take a few minutes to complete this code cell. So after running each trial, it will see whether or not that particular PCE has broken the records of the previous PCEs. If it is the new biggest PCE, it will print in the log that the new PCE is found. Otherwise, it will not print this line. So as you can see that in trial 1, it has found a new best PCE. In trial 0, it was 14.42. It is now 34.43. Let's see whether or not it improves in trial 3. So I think it has not improved in trial 2, as you can see that uh, the line is not printed after trial 2. That means that trial 2 didn't go very well. So I will pause this video and come back once it's finished. My code cell is complete, and you can see a line printed as stopping early, no significant improvement for 10 trials, which means for the last 10 trials, it did not see any improvement in its PCE. So the model has decided to stop. Remember, I have told you that it's because of this patience value. If you increase it to 100 or 1000, it will keep searching for a better PCE for 100 times or 1000 trials. So if you have a lot of HDL and ETL materials, you might want to increase this value here. So next, we will categorize the top 10 device found from the model, and it will be saved as optimized results.csv. So let's run this code. So these are the top 10 device that is found. You can see that the number one device is with titanium dioxide, CSPBI3 and Spyro OMETAD, and the ETL thickness is this. Absorber thickness, it has chosen this. HDL thickness, and the PCE it's found to be 34.47. So let's generate some plots to see what the model did. So the first figure represents the PCE progression over the trials. You can see that at around 10th trial, it's not improving the PCE, and it has found some high PCE in the early trials. And among all the trials it has run, uh, the uh, the PCE below 5 was found to be most frequent. And these are some thickness versus thickness efficiency, and these are some 4 parameter versus 4 parameter graph for more insights. And this represents the effect of dropping on the PCE. I think it's only the absorber dropping, and this is the correlation heat map of all the parameters. Since you have the updated instances with all the generated CSV file, you can do any kind of analysis with this, and we'll also have the optimized results with the device name in it. You can open it with the Excel file if you want. So one last thing is that the program actually saved a SCAPS file with the best configuration for you. So if you go in here, um, so as you can see, you will find the best SCAPS configuration inside the dev folder, and its name as the best device.scaps. So if we go ahead and open our SCAPS program, we can actually load that best configuration from here. Load all settings, and you can see that best device, and hit load, and these are all the parameters with the best configuration. uh, let's run the device once and see whether or not it has the PCE of 34%. And so it has indeed the PCE of 34%. So According to the model, this is the best configuration. So now there are a lot of room for improvement in this code. It's just uh, a starting point. It can be considered as a starting point. You can go ahead and modify and improve this code according to your need. One other thing to mention here that these results need further verification before using this code for actual research. So please verify your results before using this code directly for any research. Uh, the code will be available in my GitHub repository, and I will be giving the links in the description.